All right, today we are looking at curve sketching. So curve sketching is an application of the first and second derivative tests. And what you have here in the box, it says facts and definitions for curve sketching. I won't read all of this to you. I'll post this, a link to this in Canvas. This is meant for you to reference if or when you need it. So it is very detailed, but if you slowly read through this, you'll see it comes into focus a little bit better. So what we'll do is just go to the questions. These are guided notes, and I'll work through an example. And again, I'll post all this on Canvas. So let's just look at the first four of these. I won't read all of them, but it says if the first derivative is positive, then the function is increasing. If the first derivative is negative, the function is decreasing. If the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. So those are the parts we'll start with on these first questions. So using that or keeping it in mind, what can you conclude about the graph of a function if f prime of x is greater than 0 and f double prime of x is less than 0? So the way that we have to translate this stuff, if it's not totally obvious, this is a positive first derivative. So if you have a positive first derivative, you have positive slopes, that means the function is increasing. Okay, kind of put an implies arrow there. If you have a second derivative, so this is a second derivative which is less than 0, so that's a negative, so a negative second derivative. This means that this is a concave down function. So those are, ways to translate what you're looking at. So this, you can conclude about the graph of a function f of x. F of x is increasing and concave down. Okay, so now we'll just sketch some really simple examples of things where we're given statements like this. So it says, draw a sketch of a curve where both the first and second derivative are negative. Okay, so that means f prime of x is less than 0. So this is a decreasing function. And f double prime of x is negative as well. So this is a concave down function. So that makes sense, right? It's decreasing and it's concave down. I'm just drawing a function, whatever it is. So here's something that's concave down and it's decreasing. So when we talk about concavity, we're talking, this would be concave downward. Okay, additionally, if I added a tail here, that would be more obvious that it's concave down, but that would not just be a strictly decreasing function. Okay, well, that's going to bother me. I'll erase that. All right, next question. Draw a sketch of a curve where the first derivative is positive and the second derivative is negative. So the first derivative is positive and the second derivative is negative. So if you have a positive first derivative, your function is increasing. And if you have a negative second derivative, it is concave down. So these basic exercises are just to help you visualize what these might look like. So a function that is increasing and concave down. So it's going to go up, but it is concave downward. our next direction. So it says draw a sketch of a curve where the first derivative is negative and the second derivative is positive. So I'm going to keep writing these out even though it's repetitive. So f prime of x is less than 0, so this is decreasing. And f double prime of x is positive, so this is concave up. Okay, so it is a decreasing function that is concave up. So here is one example of that. Okay, so pretty basic stuff when you're sketching that type of function. You know, just simple functions based on statements like that. Okay, so we're going to do this example. This example, for me anyway, it's always challenging doing these. Sketch a graph of a function with the following characteristics. Typically, these questions aren't asked like this. You can't check your answer anywhere. There's no calculator you can enter it, so you just have to meet these conditions. If I were to ask you to do this on your own, which you might want to pause the video and try it on your own, you'll see that the graphs that we draw will look vastly different from one another. So that's a possibility. So I'm going to draw one graph that meets those characteristics, or that has those characteristics. So let's just start with the first line. So f prime of x equals 0 when x is 1 and x equals 5. So all that means is that we have a change of direction in the function at x equals 1 and 5. Where I put the values in the y range, I'm just putting them in places, and I may have to adjust those later. So at x equals 1, that would be a 0 derivative. So that dashed line is representing the derivative. I haven't drawn the function yet. At x equals 5, we would have a 0 derivative. Okay, put a check mark. We may have to use that information again. For the second one, it says f double prime of x equals 0 when x equals 2. So if you have a second derivative set equal to 0 and it changes sign around that value, so f, then you would have changing concavity. So this statement, the second statement, is not useful without additional information. So let's look down the list, and we have these two parts. F double prime of 0 is 1, and f double prime of 3 is negative 2. So if so at 0, f double prime of 0 is positive, so this would be concave up. F double prime of 3 would mean this is concave down. So around x equals 2, there is a change in concavity. So we call this an inflection point. Okay, so this is where it gets a little tricky. So at x equals 2, it changes concavity. So I'm just going to say, I'll put it here. Okay, so what that means is that the function is going to be concave up to the left of 2 and then concave down. So the function will do something like this. So notice that is concave down. And I'm going to do the next couple of parts first before I connect any dots. So f prime of 0 is negative 2. So at 0, we have a slope of negative 2. This is a slope of negative 2 at 0. Okay, use that. F prime of 3 is 1. So the slope at 3 is 1. So again, this represents the slope, the dashed lines, and then I'll kind of sketch around these things. The slope at 6 is negative 1. So at 6, I have some slope of negative 1. And maybe that picture's starting to make sense to you. All right, so now I need to make sure I withhold all these. So I'll sum all this up once I sketch it. So we have a function that is it's got a slope of let's see, negative 2 here, And so it's going to go something like that. And then it's got to stay concave up. And then concave down. So notice it's not perfect, but it's somewhere in there. And then it's got to follow this line with the slope of 1 with a 0 derivative. And then it has to have a slope of -1 right there. Okay, so that picture is vastly different than the first one I drew on a different assignment. And each year it looks a little different. So let's make sure that's right. So it's we have a changing concavity at x equals 2. And that one, really it's probably here on this picture, but get the idea. It's somewhere in here it goes from concave up to concave down. So I could adjust that, but that's going to be a hard one to adjust. So let's say that's good enough for now. And then I followed all the slopes, and that would be an okay picture with those characteristics. All right, this example is more similar to what your homework is like. So it says find the transition points, intervals of increase and decrease, concavity, and asymptotic behavior. Sketch the graph using this information. So it says both critical points and points of inflection won't be integers. So with all these problems, first thing you want to do is take the derivatives. So if we have, I'll just write all of these here. So f of x is 4 minus 2x squared plus 1/6 x to the 4th. So I take the first derivative, and I would get -4x plus 2/3 x cubed. And then I'll simplify that. I'll take out a 2x. And I would have 2 minus x squared over 3. Okay, so let's just work with that one first since we're there. So we have to find the critical points anyway. So what I'll do is set that to 0. So f prime of x equals 0 when x is 0. That's from this part. And then if we look at that, we would set that to 0. And with that one, we would get plus or minus x equals plus or minus √6. So those would be our critical points. What I'm going to do with this is I'll do this number line thing now, and then we'll go ahead and fill in all those parts as we have them. So we'd have a 0, -√6, and √6. Okay, so we plug in values in these ranges. So what I'll do is plug in a number between 0 and √6. Let's plug in a 1 into the derivative. So if I plug a 1 in, remember we only care about the sign. So if I plug the value 1, I would get a negative number. If I plug in a value between -6 and 0, so let's say -1, I would get a positive value. If I plug in a number above √6, √6 is just right over, just above the value 2. So I can plug in like a 3. I would get a positive number here. And if I plug in a number less than -6, like -3, I would get a negative number. Okay, so when you do these problems, just go ahead and run through all those parts, because then we're going to use that. Okay, so next, so this would be, first derivative. So next, let's do the second derivative, f double prime of x. So that would be -4 plus 2x squared. Okay, and then we set that to 0. and we get x equals plus or minus root 2. If you can't see that, just go ahead and solve it. It's just add 4 divided by 2, take square root. So on the number line for that one, we just have the values negative root 2 and root 2. And I haven't discussed any of these things from the problem yet because I have to make these number chart or number lines. I have to take the derivatives. I have to find all the zeros of each. So I'm just doing that, and then we'll go back and translate what it means. So if we plug in values into the second derivative, plug in numbers between negative 2 and root 2. If I plug in a 0, I would get a negative value. If I plug in a number above root 2, so root 2 is approximately 1.141. So if I plug in like a 2, I would get a positive number. And if I plug in a negative root 2, I'd also get, or a negative 3, I'd get a positive number. So there we have it. We have all of our sign charts and everything. So now we can start working on what this is asking. Okay, from the first derivative, we're, we take the derivative, those are our slopes. So that tells us intervals of increase and decrease. From the second derivative, we can get inflection points, we can get concavity. So the critical points, well, that's really talking about the first derivative in this case. So we would just say, well, the critical points were x equals 0 and x equals plus or minus root 6. Inflection points. So I'll highlight this as first derivative. Inflection points come from the second derivative. So if we look at the second derivative, the number chart we have, our zeros were plus or minus root 2. Does the function change sign around those? And the answer is yes, it changes sign around both negative root 2 as well as root 2. So those are both inflection points. So we would have x equals plus or minus root 2. So we have 2 inflection points. So next we have the intervals of increase. So increase and decrease, those can be taken from the first derivative. So the intervals of increase, that's where we're going to have a positive derivative values, first derivative values. So if you look at the number chart, let's number those. Number 1, we would have positive slopes between negative 6 and 0 and from root 6 to infinity. And those are our intervals. So negative root 6 to 0 and root 6 to infinity. Intervals of decrease are where the derivative values in that chart 1 are negative. So that would be from negative infinity to negative root 6 and from root 6 or 0 to root 6. Okay. Is it concave up or down? This is taken from the second derivative. It's concave up when the second derivative is positive. So from that second chart here, you can see that it is concave up from negative infinity to root 2 and root 2 to infinity. And it's concave down when the second derivative is negative, so that's from negative root 2 to root 2. Asymptotes, there are no asymptotes here, so this is just NA. Not applicable. All right, so now we have all of these things. We can now sketch the graph. So you could, what I would do is just plug in f of 0 because that's going to give us our first point. It's here. So since that is also a critical value, that means the derivative is going to be equal to 0 there. I draw that line. That's how I notate whether the derivative is 0 or not. You don't have to put that line there. So now let's see here. We have intervals of increase and decrease. So this thing is increasing from negative root 6 to 0. So negative root 6 is just somewhere, on the other side of 2 in there. Approximately, it's somewhere in there. So from negative root 6 to 0, we have a positive slope because it says it's increasing. From from root 6 to infinity, it's also increasing. And then the intervals of decrease are from negative infinity to negative root 6. And it's decreasing from 0 to root 6 as well. So that is a rough sketch of the graph with those characteristics that we can identify from the first and second derivative. So are the values all in the correct place? No, I didn't. F of 4 is probably not, whatever that is, 2. Could be, but that's not the part I really care about. I care about where does it change concavity? Where does it, if we can look at that actually. So where does it change concavity? Where are my slopes 0? All of those characteristics. So we can look though at our concavity, which comes from the second derivative chart. Those negative root 2 and root 2 are points of inflection. So that means somewhere at negative 1.41 and 1.41, it's going to change concavity. So if you look at this, it is somewhere in there. It's about, a rough estimate on the graph. But these graphs are never perfect. They are just sketches. They're just more detailed sketches than what we could do before without calculus.